Hello, Dr. Trifles here. I'm going to spend time in this video giving you an introduction to the basic concepts you will need to understand the properties of gases. This particular chapter in general chemistry books seems to be one that a lot of students have a lot of troubles with. Even though the concepts are actually fairly straightforward. I hope that after viewing and studying this video and the concepts associated with it and the next video that comes after this one, that you will feel the same way. The first thing we have to understand is that with gases we measure pressure, volume, and temperature, and moles sort of too. Those are our main variables we use to study gases. The traditional method of measuring gas pressure is the use of a U-tube manometer. The U-tube manometer is shown, a crude drawing of it is shown on the right hand side of the screen. So you have a liquid in the container, that's the hatched area, and you'll have gas on one side that's you want to know, make a measurement of, and on the other side of the container of that U-tube you will have and the tube open to atmosphere, so that atmosphere is pressing down on the liquid. Because the end of the tube is exposed to atmospheric pressure, we call this a U-tube manometer. So you can see in this case, in the hatched area again, that the level of the liquid is not the same and differs by an amount h. That difference in height tells us the gas in the container has a pressure greater than atmospheric pressure. You can actually determine what the gas pressure is if you know the atmospheric pressure. We calculate the pressure using the top equation. What the pressure is represented by the value of h. So we measure the density times the gravitational constant times h, the height of that liquid, and that can be used to calculate with the g, the gravitational constant. That can allow us to calculate what the pressure is in pascals, but a lot of times we use h and millimeters of mercury. Sometimes we use other liquids, and we're asked the question, what would it be with something like water instead of mercury? Well, you can predict that because the pressure would be the same no matter which liquid is used. The only difference would be, so g in that, and we can set the density times gravitational constant times the height for one liquid equal to the same product of the other liquid. So then you see gravitational constant on both sides of the equation, and you can cancel out the gravitational constant, leaving you with the product of density and height for one liquid equals the product of density and height for the other liquid. So we've eliminated g, and that gives us the simple equation that's described in the third equation on that on the equations listed there. It's kind of interesting to note that what has something to do with the behavior of gas. If you compare them with the densities of the liquid with the density of the gas, you can get an idea as to why substances in the gas phase might behave different from the solid or liquid. So you can see that the density of water in the liquid phase is 1 gram per milliliter. Now put that same amount of measure the density in the gas phase, and it's 1.27 grams per liter, not milliliter. So that means that roughly the volume is roughly 1,000 times greater for the same amount of water in the gas versus the liquid phase. And take the cube root of that to figure out how far apart they are, and you get an idea that they're about 10 molecular diameters apart from each other. And so because they're so far apart from each other, they don't interact with each very much. Now keep in mind they're always moving all of the time, and most of that time they will not be close to each other. We find that we can measure pressure and high temperature. This applies at low pressure and high temperature. We can describe their behavior with a single equation called the ideal gas law, PV equals nRT. So, but in the old days, people were trying to learn how gases behave. They first realized that pressure is inversely related to volume, and that is what is referred to as Boyle's law in the equation shown below the equation for the ideal gas. They also discovered that volume and temperature were related to each other in Charles' law, and they were directly proportional to each other. And then you have Avogadro's law, which relates the number of moles to the volume. And when you combine these three relationships, you can convince yourself that they are all contained in the ideal gas law, where in one case moles and temperature are constant, and so on and so forth. Anyway, the next relationship we look at here is the density of a gas. Density is the formula mass times RT over P. That's an application of the ideal gas law. It's derived totally from very simple math in the ideal gas law. So if you have density and temperature and pressure, you can very easily figure out from this relationship that we can get from the ideal gas law, we can get the formula mass. And the fact that these molecules are so far apart from each other means that they don't interact much with each other, even if the gas is a mixture of gases. So in that case, then the density can be thought of as the sum of the total pressure can be described as the sum of the partial pressures of the gases. That's referred to as Dalton's law. The total pressure is equal to the sum of the partial pressures. So we just sum each's contribution to the total pressure. And in each of these we can replace the pressure, P sub A, P sub B, etc., with the nRT over V for that particular gas. So N sub A, RT over V, etc. Now, sometimes we can do reactions and collect gas over water. It's a kind of a standard way of doing it by having an upside down burette where you collect the volume of the water. And that gas that's in the burette has gone through water, so water has vaporized, and you have both water and the product in there. And water's contribution must be removed. So we change gears here and talk about and so that makes it possible using this law to subtract that out. Next thing we do is we change gears to talk about the root mean square velocity of a gas. So we're now no longer on ideal gas. Up to this point you could say we were dealing with ideal gas. So here the root mean square velocity is equal to the square root of 3RT over m, where m is the molecular mass. So the larger the mass, the faster the molecule travels, and you can actually calculate and show that the root mean square velocity of a typical gas is on the order of several thousand meters per second. Next thing we have is Graham's law. and that states that the rate of effusion and diffusion behave in a similar manner and are related to the inverse square root of the molecular weight. The last thing on this video is the fact that when you don't meet those requirements of low pressure and high temperature, sometimes the molecules get close enough to each other that they don't behave in an ideal manner. They don't obey the PV equals nRT equation. So we have to modify it a little bit, as shown by the van der Waals equation. And that forms, so they have a slightly different molecular volume, and we have to have the little more complicated van der Waals equation where we have constants in there that are characteristic of that particular molecule, like ammonia might have an A and a B that's different from some other compounds. So I hope and think that that's all I wanted to discuss in this video, and I hope that you found that it was going to be useful in your quest to understand the chemistry of gases. I hope you have a great day. Goodbye.